All right, so let's look at sensitivity to change. In sensitivity to change, they're going to use a biological sample with genetic data and sensitivity to change. But this is actually a thing that gets explored a lot in differential equations. Um, when something changes, when systems react to that change, in a real system, there's some diffusion processes, there's some random error. What we measured initially going into the input might have an error in it. And so, the more sensitive a system is to change, the more its results might not be as predictable. In fact, chaos comes from well determined differential systems that are extremely sensitive to change. So when we talk about a chaotic system, it's not that it's random. It's a very well determined system, but small changes in the inputs or small changes in error in the system produce very divergent results. So this is example 6 in the textbook, and it's going to say when a small change in x produces a large change in the function in y, we say that the function is sensitive to changes in x. And so the measure of change, well, it's going to be our derivative, as always. Whoops, let me undo that. I didn't want a line, I wanted the line tool. So we're going to look at a function here. And what function are we going to look at? We're going to look at f of x equals 2p minus p squared. And so this is the proportion of smooth-skinned peas in the next generation, given a current generation. Now, a proportion, by definition, is between 0 and 1. So our graph here, so I'm going to have inputs and outputs between 0 and 1. And this is quadratic with a negative coefficient and a vertex at 1 and a 0 here. So we have a half parabola. Just by looking at the function, we have a half parabola. And so let's see. So Gregor Mendel recorded working with garden peas and other plants, and this was showing that if P is a number of 0 to 1 is the frequency of the gene for smooth-skinned pea, the dominant, and 1 minus P is the frequency of the gene for the wrinkled skin in peas, then the proportion of smooth-skinned peas in the next generation will be this equation. And so what we want to do is we want to look at what the derivative of this looks like. So I'll come over here. Let's see, I did, and we'll say that f prime of x will equal, well, f prime of x, this has a 1, we'll move the 1 out front, that's 1 times 2, and the 1 comes down to 0, so we get a 2 out front, minus 2p. And so its sensitivity to change, or how it will change, sorry, I did it again. There we go. And let's see here. That'll be 2. And let's see, halfway is about that far. That'll be 1. And so this function is like this. It's linear, right? It's a line with a negative slope of 2 and a y-intercept of 2 minus 2p. And so what this says is, if we look at this, the rate of change, is if your proportion is near 0, if you're over here, then the change is really, really close, or the proportion is close to 2, or the rate of change is close to 2 on this. And when you're close to 1, the rate of change is close to 0. So, right, if we peg these points here, So as you move your way out, is since this is the proportion of what is smooth to wrinkled, then what will happen is that a few more smooth skins genes into a population when the frequency of wrinkled peas is large has a more dramatic effect. So let me get my axes right here. Yeah, so when you're here, when you're out here, the sensitivity to change, if you have zero, almost zero, smooth, right? Your proportion is almost zero. Your P is almost zero. Adding a few smooth P's pushes this quickly because it's very sensitive to change near zero, right? And I guess we can kind of see it here too. If you're near a proportion of zero smooth skin, right, your slope's really large. So just a few additions in here, and you're going to have a quick rise on the triangle. Where if you're out here, your change is relatively flat based on the proportions. That's really what the sensitivity change is asking us to do, is how does it look if we move from the spot that we're at. All right, that is section 3.4. It is some applications of the derivatives that we have done. And those are the examples kind of given in the book. You're going to get a lot of particle motions, rockets moving, and you'll have some different applications presented in the homework problems that aren't always in the examples. So, I would suggest really focusing on taking the derivative and looking at it at a particular time. Once a function is given for something, your derivative is a rate of change, and you can lock it into how something is changing instantaneously. That really is what this section does, is it takes our definition of the derivative and it applies it to some specific applications.